In problem 1823, we're asked to find the average voltage at the output as well as the ripple voltage. As you can see from the schematic, this is a simple half-wave rectifier, and we've just got a 1000 microfarad capacitor across a 5K load. So where do we start in solving this problem? As always, we start off from looking at the secondary, trying to find the peak output voltage. Remember that voltage peak is equal to the square root of 2 times voltage RMS. And so in our case, that means that the voltage peak at the secondary over here is equal to the square root of 2 times 12.5 volts RMS is equal to 17.678 volts peak. This is at the secondary. To look at the load over here, it would be very easy to find the peak voltage if it wasn't for this capacitor. We know that if we did not have the capacitor there, the output voltage would look something like this. But with the capacitor there, there's going to be a change in this waveform. But we're going to just concentrate on this value over here, the peak voltage. At the load, voltage at the load, peak, is simply going to equal this voltage minus a drop across the diode. So that's going to equal 17.678 volts peak minus 0.7 volts is equal to 16.978 volts peak. So for the sake of making this problem a little simpler, let's just say 17 volts peak. We'll just say that that's the actual value here, 17 volts. Now what we'd like to do is we'd like to find out what the average voltage is, because we know that the capacitor will hold a value, but it will decay somewhat, and it will come up as it charges the next cycle. And so we know the average is in here someplace, but we don't know where it is. It's in there someplace. And we know that there is some sort of ripple voltage. Ripple. So how can we find these? Well, one way to solve this class of problems is by starting off and saying, well, I know the answer is around 17. I know 17 is a little bit high, but it's around there someplace. So we're going to just sort of say that that's true. Now, if we knew that voltage, we could find the current in here, and because we know the size of the capacitor and we know the time of this period for charging and the time for this discharging, we could take advantage of a very nice couple of equations. We could say, for example, that the voltage of the ripple is equal to the current in the load, it's the average current load, times the time of the ripple divided by C. The problem is we don't know what the average load current is. That's the real problem. So we're going to try and find it. Well, we know that the average load current, average, is equal to the voltage in the load, average, divided by the load itself. So before we can use this expression, we have to find I, which we don't know. So we have an expression here, but to use this, we have to find the voltage load, the average, we don't know that. But we do know it's going to be 17 or slightly less. So let's, for the sake of argument, let's say voltage in a load, average, is approximately equal to 17 volts. We know that that's not exactly true, but we'll say that it is for the time being. So knowing that, we can therefore say that the load current, average, is equal to 17 volts divided by 5K is equal to 3.4 milliamps. Now, because we know this, the more or less approximate load current, we can find the approximate ripple voltage. So we could say that the ripple voltage is equal to this load current, 3.4 milliamps, times the time of this period, which happens to be 16.67 milliseconds. And we divide that by the capacitance, which is 1,000 microfarads. 1,000 microfarads. We worked that all out, and that turns out to be 56.678 millivolts. So that's the ripple voltage. That's peak to peak. That's the size of this here. So we could then come along and make an approximate better estimate of the average. A better estimate, remember it is just that, it's just an estimate of the average voltage at the load. It's simply going to be voltage peak at the load minus voltage ripple divided by 2. And so we can come along and say that this is about 17 volts minus the ripple voltage, which is 56.678 millivolts, divided by 2 equals 16.9772 volts average. Now, again, this answer is not exactly correct, but it's very close to our first initial value of 17. It's fairly close. You can see it's within less than 0.1 volts of it. So we would say this answer is pretty good. If we wanted a better estimate, we would then reiterate this. That's to say, we would take this number and replace it, put it into where we had 17. So we would put this number into this expression, calculate a new current, calculate a new ripple voltage, calculate a new average value for the load. And you would keep doing that endlessly until finally the numbers didn't change anymore. But because of the fact that this number and this number are so close, we can pretty well say the answer is very close for that, for us. We can say this is simply good enough.